Thank you for your patience, everyone. My name is Samuel Hashim, and I'm the founder, one of the founders and chairman and CEO of a company called Omega Power Technologies. My background is originally a Wall Street background, and then I did nonprofit financing and built private schools. I come from an education background, and I worked with and trained engineers and scientists and placed them in various colleges and universities around the country. Today, my presentation, I'm going to introduce you to some of the latest innovative battery technology and introduce you to our company. What has made us very unique in the battery world is that the batteries that we're producing enable a cell phone to last twice as long, your EV to go 50% further in your mileage, and an aerial drone to stay in the air twice as long. And we make this possible through a novel nanotechnology.
Here, I can just do next page. Hopefully, yeah. Is that better? Right here. Is this it?
Yeah, I gotta use.
Just tell me next page.
Okay. And basically, the problem that the entire lithium-ion battery faces is the fact that the limited energy capacity is 360 milliamp hours per gram, whereas we're beginning to utilize and maximizing lithium metal battery technology at the 3,860 milliamp hours per gram by effectively and successfully cycling lithium metal rather than the lithium ion. So the industry has been limited with the smaller energy capacity that we're subject to in our cell phones and EVs and all of our applications. When lithium ion batteries first came on the scene through Sony in 1991, they very much wanted to use the higher energy density of lithium metal, but dendrite problems caused the short outs and the burnouts, and they had to opt for safety, but settle for the lower energy capacity of lithium ion. At Omega Power Technologies, we have overcome this problem through a novel accomplishment achieved in the carbon nanotube industry from Dr. Daniel Hashim, who's our chief science officer, who invented a three-dimensional carbon nanotube through a one-step manufacturing process. And what we have here is a three-dimensional carbon nanotube structure that it might not look like much. It's very thin to the natural eye, but a nanometer is 1/100,000th width of a hair, which I can't effectively illustrate to you. But so it take 100,000 of these to even see in the macro world the width of a hair, as you can see in some of the photos there. It's actually a very thick forest that effectively houses active battery chemistries, and lithium can cycle in it at a higher energy density at the 3,860 milliamp hours rather than the 360 milliamp hours, which is currently in our cell phones, EVs, and in drones today. So the companies that can effectively utilize lithium metal are going to be considered what's called the holy grail in the battery industry over the last 30 years. So when we reach the point of utilizing nanosponge as our core material, we had to then ask the question, well, we have incredible conductive material, but can in fact we create an electrode? Can we in fact create a battery? And here you can see that Dr. Hashim and our engineering battery research team have been able to put the nanosponge on a copper foil, effectively creating an electrode. And this particular battery electrode is made not just in a lab, but it's able to be fabricated to industrial manufacturing equipment. And we know that we can scale to build what's called a spool copper foil that simply replaces the graphite with a nano sponge electrode, which is really a major, major breakthrough in science technology. As you can see here, these tentacles, next slide, please, Marty. As you can see here in the tentacles, these are dendrites. And the dendrites pierce through the anode part of the battery. Next slide. There's three parts of a battery: the anode, the cathode, and in between is a liquid electrolyte separator. So what happens with dendrite growth, which every battery company needs to solve what's called the dendrite problem. And the dendrites pierce through the anode side of the battery and causes short circuiting in the separator. So after only 4 or 5 or 6 cycles from the cathode to the anode and recharging the battery back into the cathode side, after even 4 or 5 cycles, the batteries are flaming out because of dendrites. And no one's been effectively able to use lithium metal for the higher energy density. Here we see that Omega Power has effectively solved the dendrite problem. There's no flameouts, there's no burnouts, there's no electrical short circuiting in our batteries because the nanosponge electrode holds the growth of the dendrites within the sponge. This is a major, major industry-wide breakthrough and enables a company like Omega Power to utilize the higher energy density of lithium metal for the very first time. As you can see in the second slide, Marty, next slide, I'm sorry. As you can see, the top slide is a traditional battery. The white mossy filaments are the dendrites piercing through the battery after only 7 or 8 battery cycles and losing power. Here you see our nanosponge electrode battery, stable cycling over hundreds and hundreds of cycles and absolutely no dendrite growth. This then paves the way for what we need now, which is our $15 million raise that we are putting out into our Series A and our Series B to produce the prototypes, MVPs that we need for our OEM customers in the drone and smartphone space, like Apple, Samsung, and some of the drone companies that we have under NDA and letters of intent. This is a major breakthrough. So with this, we began to build coin cells, as you might know of. I have coin cells here, pouch cells, and we build a relationship with Polaris Battery Labs, is our third-party validator lab out in Portland, Oregon. And we found out later that they work with Apple, Samsung, Black & Decker, and various different battery OEMs to validate their technology. So with this, we're utilizing the Portland Battery Lab to validate our technology and the growth of our energy density. In the first, next slide, I'm sorry, Marty. Next slide. Those are all the samples of our batteries. And here's the results of our batteries. The first column, we can see a traditional graphite electrode. The black would be graphite in your current cell phone, in your current EV. We're replacing graphite with nanosponge. So here, the first column, you can see a typical graphite battery, same copper electrode, and they can maximize the watt hours per liter, which is called volumetric energy density, at about 450 watt hours per liter, as you can see here, 450. The other 3 bar charts are our 3 batteries, the best of which is the third one, all the way on the right-hand side, which is nanosponge on copper foil that you see here. And we've reached 1,000 watt hours per liter in volumetric energy. This is a huge breakthrough, my friends. That means what we are 100% increase in energy density from the common everyday battery that's in your cell phone or in a drone today. And we're 50% higher energy density than our nearest competitors in the lithium silicon space or the solid state battery design that we see in companies like Solid State Power or QuantumScape. Here you see a slide on the competitive landscape. Thank you for the change over there, Marty. And you can see here that our batteries, if you look on the x-axis, measuring the watt hours per liter that I just showed you, our batteries are smaller. We're approaching 1,000 to 1,200 watt hours per liter. And given that our batteries are smaller, when you look at the y-axis, which measures gravimetric energy density, you're looking at our batteries approaching 450 to 500 watt hours per kilogram, which means our battery is lighter and smaller, as you can see here, pictured here, in comparison to a cell phone battery. Our battery is half the size, half the weight, and double the power. This is all validated technology through a third-party validating lab. You can see here with some of our competitors in the silicon space, like Sila Nanotechnology, Amprius, they have good quality products, but they're limited in their energy density because silicon is limited. They can't use 100% of the silicon because it fragments and breaks down under the heat and pressure of cycling of the silicon ions. Whereas we can use virtually 100% of the power of lithium metal batteries. And Sila recently received $100 million touting and promoting that they have a 20% increase in energy density. And so they received $100 million through the Department of Energy recently to build out their anode, a silicon anode. Our batteries are 50% stronger than the silicon anode that they receive funding on. We have our contacts and our think tank group that we're collaborative with in Washington, D.C., who has pre-qualified us to apply for $300 million so that we could have our own gigafactory with the lithium metal cycling nanosponge batteries in our Omega branded batteries. So this is a major breakthrough for us as well. Now, when we look at the comparative to the competitors in the solid state field, right now, Wall Street and the entire battery industry, solid state batteries are said to be the future for EVs. Well, there's numerous challenges that a company like even QuantumScape has. Number one, they would have to build out their own manufacturing facility to even have any kind of volume in a solid state battery. Why? Because we're in the liquid electrolyte space. There are hundreds of batteries around the country and around the world that are using liquid electrolyte. So we could just manufacture our spooled electrode and sell that directly to them, directly to the companies that are producing EV batteries, and they can immediately have a huge volume of production. Whereas QuantumScape has to build their own multi-billion-dollar facility. This is a huge value proposition for us. As you can see here, our drop-in spooled electrode can go right into the current everyday battery manufacturing process that's in the world today without spending billions in CapEx and billions in OpEx for labor and insurance and liability insurance to build even one gigafactory.
We got a little bit more than 5 minutes.
Okay. And then here you see what's driving the market. Next slide, right? What's driving the market is there's a $25 billion commitment to building gigafactories here in the US. And more recently, there's been an additional $369 billion allocated to the Department of Energy through the recently passed Congressional Infrastructure Bill and the Inflation Reduction Act.
Is this the right slide here?
No, the one before it. Right, you can see in the right-hand side there, I'm circling it on my screen, the gigafactories, there's 25 billion, and there's an additional 369 billion now being allocated. That's the 369 billion that Omega Power will be applying for and been pre-qualified for. As was mentioned earlier today from some of the speakers, the challenge is to have gigafactories in the US and in North America to try to have our own supply chain of not only chip manufacturing, but battery manufacturing here in the US.
There's been a lot of stories in general and elsewhere just about the supply of lithium itself. I assume that's something.
Lithium is part of the rare earths that in our particular case, we're producing the electrode, and the cathode side, the battery manufacturer provides the lithium. So we don't have to handle lithium or any of those potentially flammable nickel or cobalt. That's the battery manufacturer responsibility. Does that make sense? Yeah. Here you see our pathway to commercialization, and the Series A round enables us to produce the MVPs we need for Apple, Samsung, and some of the drone manufacturers that we have. The Series B round for 5 million enables us to produce the spooled copper foil that will enable us to sell directly to our drone manufacturers. Next slide, please. When you're looking at the go-to markets, next slide. When you look at the go-to markets, what drives the market right now is EV production of batteries. And what I'm holding in my hand right now is a 25-650, 22-650, and a 25-650. It takes 6,000 of these batteries for one electric vehicle, and it's sold for $130 per kilowatt hour. The 25-650s, maybe it'll take 5,500 batteries in the base of that vehicle, sold again at about $130 per kilowatt hour. Whereas, if you would use a, you'd see a smartphone battery, like this right here, the smartphone battery, you sell one of them to Samsung, one of them to Apple, put into one cell phone, and you could purchase that for $900 per kilowatt hour. 6,000 of these for $130 per kilowatt hour. One of these for $900 per kilowatt hour. For a drone, one of these for $4,000 per kilowatt hour. So our first initial go-to market with this raise of $15 million enables us to sell 3,000 to 300 to up to 1 million single batteries to drone manufacturers and immediately get to revenue at $4,000 per kilowatt hour. Our second go-to market will be the drones. Will be the smartphones at $900 per kilowatt hour. By that time, our technology is proven, and unlike our solid-state competitors, we will produce our spooled nanosponge electrode and sell that to the entire globe and to the entire US gigafactories that are coming online for direct market penetration into the EV market. But we have to be strategic and we have to be smart about our go-to markets.
Only a couple of minutes left.
Couple of minutes left, thank you. Here you see our market value potential. Next slide, Marty. I'm done with this.
This one here?
Yeah, this will be my final slide. With the $15 million raise, $5 million of which goes towards the manufacturing of our Series B, the third bullet up here that I'm circling, we would have a capacity of 70,000 kilowatt hours capacity. And if, let's say, our first year of production, which would be 3 years from the time of funding, let's say we were only able to manufacture 4,000, the first column, 4,000 kilowatt hours, which would be only 300,000 battery units for the drone would be 300,000 of these. It would be $4,000 per kilowatt hour, as you can see. The battery itself will cost about $52 and generate about $16 million in revenue. We would still have 66,000 energy capacity in our little manufacturing plant. So let's say first year we were able to do column 3, 36,000 kilowatt hours, which would be about 2.75 million of these batteries, which is still only 1.5% of the market. Gives us $144 million in potential revenue, and that's still only half of our capacity. Let's talk about a quick, and I'm done, Marty, I'm sorry. Let's talk about a quick blue sky scenario. Remember, our first go-to market is these. Second, cell phones, okay? The fourth column shows a little bit of the blue sky. Let's say we have the 300 million. It's going to take 12 months to 18 months to apply for the 300 million that we've been pre-qualified for already. And so the fourth column will be drones and smartphones together. 36,000 still only do half of our capacity, and 3 million would be the maximum capacity of the new gigafactory. Would give us over $1 million in smartphones and drones. This will enable us then to create on a larger scale the higher volume of our school electrode to go directly to all the gigafactories around the world for our EVs, because we would have had a proven product. And so we're seeking the one more slide, Marty. I'm sorry. It'll show the rates, and then I'm done. I promise. I'm sorry about getting off to such a horrible start here, guys. Terrible. But so we're seeking the 15 million for 20% equity. It's a 2-year projected use of funds. You see the Series A at 10 million for the prototypes, and the Series B at the bottom half is the 5 million that enables us to scale our carbon nanosponge electrode at 70,000 kilowatt hours. The pre-money valuation is 60 million. We've raised about 4.5 million under a seed round, and now we're going into this current Series A and B round. Thank you so much for your time and your attention, and sorry for getting this off. It's such a horrible start.
Okay, one question. I see that there are these electric cars that seem to have fires. Does this dendrite reducing technology
Eliminates, and plus the liquid electrolyte that our engineers will use and fabricate is a non-flammable electrolyte, which enables us to stay in the current gigafactory world that we're living in, that lithium ions are now cycling, but we can cycle lithium metal at the higher energy density and sustain high volume for an EV to go 50% longer in their range of mileage with our battery.